All right, so the first thing I wanted to talk about today is an acknowledgement. Oh, excuse me, I think my iPad just stopped. 1 second. Is an acknowledgement that our most recent homework was very, very difficult. So please, if you found it difficult, know that you are by no means in the minority here. It's one of those things that probability problems like this, they can be a little sink or swim, and one of the best ways to learn is to just kind of wrap your head against the wall, but I may have overshot a little bit with how much I can expect you all to wrap your head against the wall until you fully understand these pretty difficult problems. Um, that said, I'm very pleased with how all of you handled it. I think people really gave it a really good try, and if they struggled and needed help, they came and got help, which is ideal. That is very much what I wanted you to do, and I'm very pleased. However, based on the feedback I've received, I'm going to be going over some of these problems for basically the first half of this lecture. To sort of give us some more examples on, with this sort of problem, this is how you would approach it, and this is how you would solve it, specifically when talking about expected value with variance. So I have two kind of hefty examples we're going to start by going through. And please, if this homework really hit you and you have yet to figure out those problems, please come and see me in office hours. And I'd even be willing to meet with you outside office hours if you really want some one-on-one time to just hammer them through. I'm here to help you figure this out, and it was a hard homework. So congratulations on getting through it. And know the ones in the future are going to get a little easier. So this really was the hard one. Okay. So let's talk a little bit more about expected value and do some examples with it. So I'm entitling this using expected value to make this and variance to make decisions. And actually, I am going to talk to you all about something in my life that I'm trying to make a decision, and you all can help me actually calculate whether or not I should do it. And this might be a little TMI about Murph. Not gross, but you'll see. 1 second. I am considering, and this is true, entering a raffle held by my tattoo artist for free tattoo time. And here are the details. One entry costs $80. I know that 20 people have already entered. First prize, my tattoo is free. Second, I get a discount, and it's only going to cost me $130. Third place, I get a discount, not quite as much. It's going to cost me $530. Fourth, fifth, and sixth places, it looks like I think I'm going to get a very slight discount and have to pay $830. And if I lose, I pay the full price, which is $930. So, should I or should I not enter this raffle? So there are two decisions. I can either enter it or I cannot enter it. So let's write that out. Let's say decision 1, enter the raffle. In decision 2, don't enter. So note, let X be the amount I pay for my tattoo. Ah. Okay, so if I do decision 1, or decision 2, the expected value over the long term of what I pay for my tattoo for decision 2 is pretty easy. It's just $930. There's no randomness involved. I didn't enter the raffle. I would just pay the full price of the tattoo, $930. And the question is, what is the expected value, the long term, of what I would pay if I did decision 1? Well, the first thing you should do is just write out your probability distribution. So the different values X and the probability of X. So if I win, I only pay $80, right? I paid the $80 at the beginning to enter the raffle, but then my tattoo is free. So X is equal to 80 with a probability of 1/21. Since 20 people entered, if I also entered, it would be 21. So a 1 out of 21 chance that I win the game. I get first place, okay? If I get second place, it'll be, I get a big discount, so it's 130, and then I have to add the $80 I had to spend to even enter the raffle. So that is what? I pay 210 with a chance of 1/21, right? And then so on and so forth for the other options. For third place, it would be.
Will you say where you got the 1 out of 21 from?
Oh, of course. So there are 20 people in the raffle. If I enter, there are 21, right? Only one person wins first place. So I have a 1 out of 21 chance, given that everyone has an equal chance of getting first place, Make sense? Okay. So 210 is 1 out of 21. The other option I think was 530 I would pay, and then I think I also would pay the 80, right? So it would be 610. That would be third place. Fourth, fifth, and sixth place looks like I'm paying 910. And those are 3 places that cause that. So 21. So fourth, fifth, and sixth place, 3 of the possible 21 people will get those. So that happens 3 out of 21% of the time, proportion of the time. And then if I don't win, I'm actually going to pay the full price, $930, plus the 80 I spent on the raffle ticket, which is $1,010. Oh my gosh, that's so much money. So can anyone tell me, so this would be otherwise, right? Can anyone tell me what the probability of this last event is? So what's the probability that I don't get any of these?
Is it 15 out of 21?
Oh, it is, exactly. Very good. It's specifically like the amount left. If 6 people get one of these prizes, then the remaining 15 people didn't get anything. And if I end up being one of those 15 people, then looks like I lost some money. Okay? So this right here is our probability distribution. That's what we would call it. And once I have it, it's pretty straightforward to calculate expected value. Or maybe I shouldn't say pretty straightforward, but use this equation. Which in this case, let me see if I can get it all on one screen, is 1 over 21 times 80. And if someone could do me a favor, you want to put this in the calculator while I write it out to save us some time? Times 1 over 21 times 210 plus 1 over 21 times 610 plus 3 over 21 times 910 plus 15 over 21 times 1010. Okay, can anyone tell me what my expected value is?
I have a question.
Of course.
Why does it continue to be 1 over 21 for like second place and third place? Because the first person can't win again, right?
You're right. That is an excellent point. And in fact, it was a bit of a simplifying assumption that I made.
Okay.
So I want you to think about it in terms of the roulette wheel. Yeah, actually, that is the more complicated way to do this, and that really is how you should do this. So I guess we should change it up a little bit. Give me a moment. Let us assume, for the sake of this problem, that you can win more than once. But you are correct. Without that, this problem becomes more complicated. Thank you for that. No, it's good. I should have thought about that more before I use this example. All right, so given that I could win more than once, what can somebody tell me what this summation is?
I got 894.
Okay. Wait, is that actually true? Wait, actually, I take it back. I think this still works if I'm only allowed to have one of these options. Because you don't want to frame it as I'm drawing a person and then I'm drawing another person and I'm drawing another person. Frame it more of I'm going to fit into one of these categories. Does that make sense? Like if these were all slots on a roulette wheel and I'm the ball that you're rolling around the roulette wheel, I'm going to fall into one of these categories. One is first place, one is second place. A bunch of you don't win at all. Does that make sense?
Yes, it does.
It's an excellent point. I'm really glad you brought it up because it makes you kind of think a little bit. Does this really work? But this does work. And thank you. Oh, wow. This didn't come up in the last class. Nobody asked. So very astute of you. So this does work. Excuse me. And this is my expected value of the price I pay if I make the decision to join. So look at this. Decision 1. My expected value of X was 930. Decision 2. 894, right? So I'm going to tell you.
Reversed? Didn't you
What?
say that? Didn't you say decision 2 was
Did I
9?
get these mixed up? I very much did. Thanks for the catch, Anna.
You're welcome.
All right, let's just put these. Yeah. So according to this, and I'm going to talk a little bit as to why you should go with this decision, but I should go with decision 1 because it has a better, my goal is to spend less money, so it has a better expected value, which means actually right after this class, I'm going to buy a raffle ticket. So thank you, everyone. You can send me a bill. You can send me a bill in the mail for helping me out.
Best of luck. Best of luck.
Thank you. Lady Luck should be on my side. However, I need to make an important note about this. So expected value is how much I expect to pay over the long term. This does not mean I am going to pay less. But rather, if I were to do this raffle many times, I would pay that much on average. So the question is it really, should expected value really like determine what your decision is, right? Because I'm not doing it over many times. I'm gonna do it once and never again. So what I wanna give to all of you is actually a little bit of a life philosophy. So maybe something you can take away from this class. Over the course of your life, if you make the better expected value decision, you'll average out to doing better if you hadn't. Okay, so for me, it's a bit of a life philosophy, right? I'm not necessarily expecting to pay less money on this particular raffle situation. But over the long term, if I keep making these decisions that have the lower expected value, if I let that drive my decisions, then that is like repeating sampling, granted of different variables, but I don't know. For me, it's sort of like this, it'll work out in the long run kind of philosophy. Not necessarily, I'm gonna buy this travel ticket because it's gonna save me money this one time. Because, you know, it might not. A little caveat on this. Do consider the risk, though, which I'm going to talk about in a second. So something to think about. I'll come back to this sort of life philosophy of mine.
I have a question.
Of course.
So like in the case of like you're only going to be entering this raffle once.
Yes.
Like what does the expected value mean then? Like for you?
Not the answer to your question is not much.
Okay.
Because I guess it's an expression of why don't we think about it this way? Since it is only a single entry into this raffle, look at my probability distribution. I'm losing money 15 out of 21 percent of the time, and I'm gaining money, what is this, 6 out of 21% of the time. So since I'm only doing a single draw, right, my probability of losing money is greater than my probability of saving money, right?
Right.
The thing that makes the difference is the amount that I save when these rare events happen is enough that if I did it over and over again, once or twice or 3 times, I'm gonna save a lot of money, and that's gonna make up for the money that I lost all those times that I lost, right?
Mhm.
So I'm using expected value to drive my decisions in a case that maybe it really shouldn't, but I'm arguing that my life philosophy is just go with the lower expected value because it'll all wash out in the end.
Gotcha.
Which you may or may not decide to join me in this grand gamble I'm making. But no, your question is excellent. Really, I should be saying, 6 out of 51% of the time I'm going to make some money, and all the other times I'm going to lose some money. So thanks for bringing that up. All right, so that was my example number 1. That is just doing expected value, and I thought it was kind of cute that I did it in a real world scenario. But let's talk a little bit more about expected value and variance using those identities that I went over at the end of last class. So let me grab those identities. So I'm going to actually just write these down. So recall our identities. Oop, not X, A. Plus E of Y. I'm going to skip that one. I'm going to say variance. Again, where A is a constant. And this one, which is very much a very important one, is independent of Y. Look, I used that shorthand. I promise I wouldn't, but I did it anyway. Okay, so keeping these in mind, I'm going to scroll back up to them a few times as I go through this example. Let's talk about Easter. In the Greek Orthodox tradition of Easter, followers play a game with red eggs. In the game, one tries to crack another's egg with their own. Having your egg cracked means you have to eat it. So this is a certain version of the game. I have a friend from Greece who I was asking about exactly how this is done. And he said you eat, he says you eat it, but I think other people, you don't necessarily eat it. You like, there's something you shout whenever they get cracked. But this is the game. And we want to let X be the number of eggs you eat. On Easter. So let's write out our probability distribution. X can take on a few values. Say you eat no eggs. You did very well cracking other people's eggs and having your egg be uncracked. You eat 1, 2, or 3 eggs. And I'm going to say you eat 0 eggs with a probability 0.15. You eat 1 egg with probability 0.5, 2 eggs with probability 0.3, and 3 eggs with probability 0.5. So I hope we kind of get this by now, but the expected value calculation is pretty straightforward. It's 0 times 0.15 plus 1 times 0.5 plus 2 times 0.3 plus 3 times 0.05. And this actually is just 1.25 eggs. So if I were to play this game over many, many Easters over my entire life, year to year, I would expect the average amount of eggs I eat every year to be 1.25. Let's talk about the variance of x. Well, this was that formula. I think it looked, right, excuse me, I know it looked like this. Of xi minus e of x squared times probability that x is equal to xi. And I'll write that out. In this case, it looks like 0 minus the mean that we calculated, 1.25, squared times this probability, plus 1 minus 1.25, squared times this probability, plus 2 minus 1.25 times the probability of 2, which is 0.3, plus 3 minus 1.25 times the probability of 3 squared times the probability of 3, which is 0.05. Okay? And if you were to calculate this out, you are welcome to check my math, but I got this. Okay? So this is me every year. I have the same probability distribution of how many eggs I'm going to have to eat. And I have calculated variance, which, as we recall, is an expression of spread, of how spread out the values are. So we were able to calculate this with our taking like a sample of octopus tentacles, right? They had a bunch of different values, and we could talk about how wide, in what range, what is the spread of those values. In the case of a random variable, we can think of variance as and standard deviation. We kind of use these interchangeably, but we can think about these quantities as an expression of risk. So this is how we would do it for one person. Say another person let me do it this way. Say the amount another person eats is y. And they expect to eat year to year if we looked at their probability distribution, which I'm not going to tell you because I didn't bother writing one out. But say over the long term, they also expect to eat 1.25 eggs, but their variance somehow is actually 2 eggs. So let's draw a picture of these. Or actually, I think I'm going to be a little bit less heavy-handed and say their variance is 1 egg. So we'll call this x, and as we noted, x had an expected value of about here, right? And there were certain values that x could take on. It could be 0, it could be 1 or 2. Could I eat 3? Yeah, I also said 3, right? So X sort of had this spread, right? My expected value over the long term is 1.25, but I could see me eating 3 eggs. I could see me eating 0 eggs from year to year. Having a larger variance in this context so for Y, they had a larger variance, but their expected value was the same, right at 1.25. Having a larger variance basically means that the values that you can take on are more spread out, and the probability of them is not negligible. So in a way, Y has a higher risk because there is a chance they'll eat a lot of eggs. Of course, this is assuming that you don't want to eat eggs, but so I guess you have to think about it the other way around if your goal is to eat as many as possible. You can think about this also in the context of stocks. If you take on a lot of risk with stocks, put a lot of your money into a very volatile stock, well, you kind of have this high risk and high reward situation. There's a risk that you're going to lose all of your money, but unlike the person who invested in bonds, you have a chance of making a lot of money as well. So Y has a greater variance, just like just like investing in stock would have a greater variance. The money you make by investing in stocks has a greater variance than the money you would make by investing in bonds. So getting back to my philosophy about always going with the thing that has a lower expected value, yes, but you should also consider risk. Because if you do that one trial of something that loses you all your money, maybe you should have considered the risk before you made that decision. So I bring this up because I've introduced this calculation of variance for random variables. I think expectation has a decent interpretation and intuition about why we might want to calculate that. This is the reason we might want to calculate the variance of a random variable, because it tells us how much risk we're taking doing this decision over and over again. So if you're only going to do this decision maybe like one time and it had a really high variance, it might not be the best decision to make. Wow. So that's a bit of the interpretation of variance. I'm now going to go a little bit more into what caused people trouble on the homework, which are applying these different identities. Okay? And I'm going to continue with this egg example. I think it's useful for this. So suppose this year, the stakes have risen. I have to eat 3 eggs whenever my egg is cracked. Actually, I just realized that's a bit of double entendre, because I think that's one of the things that they say in Easter is he is risen, except now the stakes are risen. Okay. So what you would do in this case is the amount of eggs I eat is now 3 times x, right? Whatever my normal outcome would be for x, whatever that is now increased by a factor of 3. And in this case, if I want to know the expected value of how many eggs I eat now that, in fact, maybe I should say this, from this year forward, So the amount of eggs that I eat from now into the future is, I want to know the new expected value. I would just need to know the expected value of 3 times my old probability distribution x, my old random variable, which, using one of our identities above, we are allowed to just move the constant out. This is going to be 3 times 1.25, or 3.75 eggs. Right? It's pretty straightforward. In this case, if I wanted to know my new variance, my new risk, which, think about it, I would expect risk to go up because I suddenly have a much wider range because I'm dealing with like 0, 3, 6, 9 eggs eating. Oh my gosh, eating 9 eggs. What you would do is you would use, here, let me write this. Use this identity. Which would give us and actually the units here is eggs squared. Okay? So that's how we do this problem, and it has a little bit of a nuance. It's related certainly, but it is distinct from this problem, which is 3 people play the game. Independent of one another. So the outcome of one person doesn't affect the outcome of another person. And they all have the same probability distribution. So they all get, what was it, like 0.15 of the time, they all get 1.5% of the time, and so on and so forth. So what's I want to know about, okay, why did I write that way? I want to know about the total number of eggs they eat. Okay? So this is actually pretty straightforward. You start by kind of defining your random variables. Let x1 be the number person 1 eats, number of eggs. X2 to be the number of eggs person 2 eats, and x3 to be the number of eggs person 3 eats. So if I want to know the expected value, for example, of the total number of eggs they all eat, that would just be the expected value of x1 plus x2 plus x3, which I can use our identity from above to say this is just this. Which is just, what was it, 1.25 plus 1.25 plus 1.25, or 3.75 eggs. So in this case, the expected value is actually the same as in our previous case. The major nuance here happens with the variance. So if I want to know the variance of the total number of eggs they eat, I can use this identity. If they're independent, the variance of a sum is equal to the sum of the variances. So we have the situation, right? And the variance of each of these is all the same. They're each 0.5875. So this is equal to 0.5875 plus 0.5875 plus 0.5875, which, oh my goodness, let me see what that is. I'm getting it is 1.7625 eggs squared. So notice the answer to these problems is not the same for variance. If I am dealing with a situation where it is the same random variable just times by a constant, so it is just me cracking eggs, but whatever the outcome I get, I times it by 3. In that case, we pull the constant out and square it. If it is the situation of 3 independent trials, 3 different people cracking eggs, and I want to know how to add them up, in that case, you need to use the fact that they're independent to split up the variances and then just add them together. Also, as a note, if you wanted the standard deviation here of the sum, just use the fact that it's the square of the variance to do this. Which we just solved what that is. It's 1.7625 egg squared equals this. All right. All right, so that was another one of example. That was our first example of using the identities. I have one other little one, and then we're going to talk about the binomial distribution, and we'll be done for today. Do we feel good about this? Yeah? Sorry if this is a tad banal, but I think it's also evidence from office hours. I think we just needed more time to talk about these and go over them a bit more. I post all these notes, so if you don't understand anything, you can look at them and kind of try to walk through my steps at your own pace. And of course, I must reiterate, I'm more than willing to meet with you one-on-one or during office hours. So, suppose I wish to compete with my friend. I want to know how often her egg consumption exceeds mine. So let x1 be the number of eggs I eat. X2 be the number of eggs she eats. And x2 minus x1 would therefore be the number she eats more than me. Make sense? So, over the long term, how many do I expect her to eat more than me? Well, we can use our identity to just say this. Okay. And This was 1.25. This was also 1.25. So unsurprising. If we have the same probability distribution, over the long term, we're going to be eating the same number of eggs, and it's not a really great competition. However, there's something interesting that happens with the variance here. 2. Okay. And let's say they're independent. Sorry, maybe I should have said that. Independence. Notice we can rewrite this in kind of a clever way. And from here, we have the sum of 2 random variables. And from here, we can split them apart. Do you see it? And I'm going to be using another one of my identities, which is if I have a constant, which is what this is, in front of a random variable in the variance, I can pull it out and square it. -1 squared is just 1. So this is actually equal to this. Pretty cool, huh? The variance of the difference actually ended up being just the sum of the variances rather than the difference of the variances. Okay? How do we feel about this one? This is my last little example. Okay, cool. So that was that. Let's move on to the binomial distribution. Cool. So fun little fact. I don't know if any of you have ever read Sherlock Holmes, but Professor Moriarty, he actually, in the story, he apparently does his thesis on the binomial theorem, which is, it's sort of interlocked with this thing, the binomial distribution. So whenever I was an undergrad, my abstract algebra teacher would call the binomial theorem Professor Moriarty's theorem, which I always thought was kind of fun. If any of you get the reference. So maybe in his honor, I'll call this Professor Moriarty's distribution. Only because that's a very fond memory for me. Okay, let's talk about it. So suppose, let's try to explain what this is by means of an example. Suppose 6 people take a very difficult test. Where the probability of any of them passing is 0.65. Okay? What is the probability that 3 of them pass? You could also ask, what is the probability that 4 of them pass? None of them? So I'm going to dive into this in a sec, but first, let's define a random variable. Let x be the random variable of how many people pass. So my above little points are the equivalent to saying, what's the probability that x equals 3? What is the probability that the amount of people that pass is 3? What's the probability that x equals 4? Right? These are the questions that I'm asking. And based on what we have talked about so far, we could solve this using logic and a bunch of grunt work, right? You could think about what are the different possibilities, what are the different number of ways that 6 people can take an exam, and maybe this person passes and this person fails and then this person passes, and you can think about the whole sample space, and then thinking about the proportion of the instances in that sample space where 3 of the 6 people pass, right? But as I hope you have realized from your homework, this is a very difficult thing to do, and it requires a lot of thought and effort. And what I'm going to tell you is there is a formula for this. For this very particular probability problem, if you can recognize that a problem fits into what we call a binomial distribution, which is what this is an example of, you can use the following formula, which is P x equals k equals n choose k. This is a binomial coefficient, this little thing I just wrote out, but I'm going to explain what it is in a second. So hold on, hold your horses. X choose k, p to the k, 1 minus p to the n minus k, which is equivalent to n factorial k factorial n minus p, excuse me, n minus k. Factorial p to the k, 1 minus p to the n minus k, where n equals total number of people taking the test, p equals the probability of success, and k, of course, is like our input. With what probability will k people pass? Okay, so the idea here is rather than think about the sample space and calculate the proportion of events and divide by the total number of events, total number of things that could happen in our sample space, which is how we've kind of been approaching these probability problems. If you can recognize that a problem sort of fits into this what we call a binomial framework, it follows a binomial distribution, then you can just say, oh, well, my p is equal to 0.65, my n is equal to 0.6. If I want to know the probability that x equals 3, I just plug 3 in for k. And I'm going to show you how to do that. I have a number of examples we're going to walk through. But first, I've given you an example right here of what a binomial distribution is. I want to define it in generality before I move forward. So, definition of a binomial distribution. When a random variable x describes n independent trials, independent binary trials where each trial has a probability of success has a probability, which we're going to call P, so probability P of success. We call this random variable binomially distributed. All right. So let's do an example. So it's a distribution. There is actually a picture, which I'm going to show you in a second, which is this. So note this isn't a density curve. This is more like a histogram. It's a scaled histogram, right? We'll call this binomial. And since it's sort of a discrete, it has discrete outcomes because, you know, we're not going to get 1.5 people who pass the exam. It's either 1, 2, 3, 4, 0, et cetera, et cetera. The way you would read this is the probability that 2 people pass the exam is, well, it looks like it's like 0.09, right? Probability that, oh, excuse me, oh my goodness, that would be the density. Who am I kidding? Wait, actually, it wouldn't be the probability in this case. Wow, I'm getting mixed up. Yes. In this case, it would be the probability of x equals 2 equals 0.09, but I'm going to get a little bit about how you should actually view this histogram in a second. Let me introduce my example before I talk about that. So let's do that one I spoke about before. What's the probability that 3 people pass the exam? Well, according to our formula, if I want to know the probability that 3 people pass, the probability that x is equal to 3, I can actually just plug the values in. So recall, I'll write it again. This is so in our case, there are 6 total people taking the exam. The probability of success is 0.65. In our case, 3. So we just plug it in. So what is this? 6 choose 3, which is in 0.65 to the k, which is 3. It's 0.65 to the 6 minus 3. 1 minus. Oh my goodness. I'm making so many typographical errors today. Which is just 6 factorial over 3 factorial, 6 minus 3 factorial. So 1 minus 0.65 is 0.35, and I want to take it to 6 minus 3, which is the 3rd power. You see it? So what is this? This is 6 times 5 times 4 times 3 times 2 times 1. That's how a factorial works. And 6 minus 3 is 3, so it's 3 factorial, 3 times 2 times 1. Looks like these cancel out. This is 0.0145. And if I work it all out, I'm going to get 0.23549. So frankly, that's the answer to this problem. If you were in this situation, if you were trying to solve this probability problem, if I asked you what's the probability that 3 people pass the exam, boom, it's right there. It's 0.23549. Over the long term, that's the proportion of times that'll happen, which is kind of cool. We didn't have to think about sample spaces. We didn't have to logically reason what it should be. We just have to plug it into this formula. So hopefully this will make these problems a little easier for us. Another example. what's the probability that 2 or fewer pass? Okay? And let's think about our different options of how we could solve something like this. We have a density curve. Let's look at the area beneath it. Oh my goodness. That's this right here, right? So what, I know that probability at x is less than or equal to 2. That's probability of x is 2 or fewer. Well, that's just going to be the area here plus the area here plus the area here, right? Just like all of our area under the curve calculations we've done so far. So the base here are all 1. And let's see, I think this one looks like about 0.09. This one, I made the guesstimate of 0.02, and this one looks like 0.001. So that means, according to my area under the curve, I'm going to do 0.09, which is the area under the first bar, 0.02, the area under the second bar, 0.001, area under the third bar. Looks like I'm getting 0.111 is my answer. So, you know, it's a bit of an estimate because I'm kind of like trying to see, ooh, what number is really there. We can do so exactly, though, using the formula. So what's the probability that x is 2 or fewer? Well, this is going to be equal to the probability that x is equal to 0, right? Nobody passes. Or the probability that 1 person passes, or the probability that 2 people pass. And note something really cool, that these events are disjoint. Right? If 1 person passes, we can't have the outcome that 2 people pass, right? One or the other needs to happen. They're implicit that they're disjoint. If I know that nobody passes, I can't also have that 1 person pass, right? Does that make sense to people? I'm kind of being hand wavy, but I feel like that's pretty intuitive. So because they're disjoint, that's just equal to this. Which, if we plug all of these into our formula, which I will leave you to do so yourself and verify my results. But when I did it, I got these, which add together to get us this. Yeah, so our guess right here was pretty close. Of course, I was kind of doing it like, it looks like it's here, it looks like it's here. But it looks like we made a pretty good guess because this is the exact answer. All right, so that's how you would solve one of these problems. I want to give, let me see. So I'm gonna give you all time. I'm gonna end early so you all have time to watch the lecture video, but I would like to give you another example. Oh, I have 2 other things I need to mention. So a quick example, because this is gonna help you on your homework. So I wanna make sure to give it to you. And that is, of 5 or fewer people passing. Well, we could solve this the same way we solved the previous example. This is, which is equal to the probability that x equals 0 or x equals 1 or ... x equals 5, right? Which we would use disjoint to split these up. And this would certainly give you the answer. The thing, though, is that you would have to use that formula, what, 6 times? Which is a little cumbersome. So what I want to say to you is that let event A and event B and note that event A and event B are disjoint events, right? Since 0, 1, 2, 3, 4, 5, and 6 are the options of how many people could pass this exam, if 0 through 5 is in event A, if event A doesn't happen, event B must happen, and if event B doesn't happen, event A must happen, and they certainly can't both happen. So these events are disjoint. So by law 4, okay? Which means if we wanted to know the probability that x is less than or equal to 5, well, that's the probability of A, which is equal to the probability of x, which is equal to 1 minus the probability of B that I just argued, which is equal to 1 minus the probability of x is equal to 6. So we took having to do the formula 6 times, and we instead figured out a way of having to do it 1 time. Just take 1, do it 1 time, and then take 1 minus that value, right? And I bring this up because I believe there is a problem on the homework where it would take you a very long time to do it if you didn't realize you could just look at the complement. Okay? So this is my little homework hint because I don't want them to be as hard as the last one. Yes, Anna, what's up?
Yeah, you don't know what that number is, right? Do you know what that comes out to be, just so that we can go back and
Probability x equals 6, you mean?
yes.
Oh, sure. I can go through it. Why not?
Okay.
So that means that, so let's just start by finding what this is. So what is our, by the blah, 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 blah. Formula is this. So 6 is our n. Our k here is going to be 6 as well. .65 was our p based on the problem. Okay. So this is 6 factorial over 6 factorial. 0 factorial is actually equal to 1. Just here, I'll write that out. That's a fact just from algebra. Times 0.65 to the 6th times 0.35 to the 0. Also, anything to the 0 power is equal to 1. Again, these are algebra things that I assume you all know. So let me find out what 0.65 to the 6 is 0.0754. So that's probability x equals 6. So thus the probability that x is less than or equal to 5 is equal to, which is okay. Nice. Yeah, thanks for making me do it. So one other comment. And then I'm going to release you. Just like any other random variable, x has an expectation, and a variance. Right? This is the random variable of how many people pass the exam. And if we wanted to, we could use our formulas to figure it out. Right? But you don't have to. And that's because just like there was a formula for the probability of x is equal to k, there are also formulae for the expected value and the variance of x when x is specifically one of these binomial distributions, right? When x specifically describes this process of a multiple independent binary trials. And I'm just going to give it to you. If you want to know the expected value of a binomial distribution, it's just n times p, the number of people taking the test times the probability of succeeding on that test. The variance of x is np times 1 minus p. Again, if you're ever asked for the variance of something that's binomially distributed, you can just take p, the probability of success, take n, put them together in this way, and boom, you're done. And of course, as always, the standard deviation of x is equal to square root of the variance of x. Okay? So if on the homework, it asks you for an expected value of a really complicated process, as long as you realize that that process fits into this sort of binomial framework, it's a very easy problem. Of course, if you don't realize that, it's a very hard problem. So was it really easy in the first place? Who knows? So that is actually, oh, sorry, go ahead.
What exactly is that binomial framework? Like, we went over examples, but like, how can we see something and be like, oh yeah, that's binomial?
That's actually, it's a good thing to talk about, but I did give a definition of it. It is when there are n independent binary trials where each trial has a probability p of success. So my example was 6 tests and each person has a 0.65 chance of passing the test. But you could think of many different ideas. I think flipping a coin 20 times and asking what's the probability that I get 10 heads. That's a probability n equals 20, p equals 0.5 problem. Does that make sense? But this right here is the general framework. If you can rephrase the problem of fitting into this definition, you are able to use this formula.
Perfect. Okay? Thank you.
You hopefully will get more practice with this on the homework, and perhaps in future lectures I will give you more examples. But this is sort of a quintessential example, and now we gotta get our hands dirty thinking about it. So that is the last thing I needed to cover for this lecture. You may go if you would like to, but I'll also hang out and answer any questions that any of you have.